You probably think concrete is just dry, solid, kind of boring, right? Well, what if I told you that deep inside the sidewalk you're standing on, there's a microscopic ocean just teeming with chemical reactions? Today, we're going to dive into that unseen world and uncover the secrets that literally hold our cities together.
So, what is really going on inside this thing that seems so simple? It's not simple at all. It's a microscopic metropolis. And, understanding its secrets is absolutely the key to building a stronger future. So, here's the roadmap for our little journey. First up, we'll dive into what I'm calling concrete's chemical soup. Then we'll investigate its hidden architecture in a tale of two pores. After that, we're going to uncover the 4 hidden forms of water. Yeah, you heard that right. And finally, we'll zoom back out and connect all this tiny stuff to the world around us. All right, let's kick things off with something that might just blow your mind. Concrete is never truly dry. Nope. Inside every single block is this inner ocean where chemical reactions are constantly happening, even years and years after it's hardened. Now, this inner ocean has a proper name, of course. It's called the Pore solution. And listen, this isn't just leftover water from when it was mixed. It's a really complex chemical bath that forms as the cement compounds dissolve. And it's the arena where the real long-term chemistry of concrete plays out. So what exactly is in this chemical soup? Well, while a lot of different ions are kind of swimming around in there are 3 main players that stick around for the long haul. We're talking sodium, potassium, and hydroxyl ions. These 3 basically define the concrete's chemical environment for decades to come. Okay, but why should we care about these ions? I mean, sodium, potassium, who cares? Well, here's why it's a huge deal. They make that pore solution electrically conductive, kind of like salt water. And a more conductive solution acts like a highway for corrosion, especially for the steel rebar that gives concrete all its tensile strength. This is a direct line from nanoscale chemistry to the lifespan of a massive bridge. It's incredible. And this is where modern concrete gets super, super clever. What engineers do is they replace some of the cement with other materials, things like slag or fly ash. By doing this, they're essentially diluting that chemical soup. It lowers the concentration of sodium and potassium, which makes the whole solution less conductive, and that dramatically slows down corrosion. It's genius, really. All right, so we've waded through the chemical soup. Now let's grab our virtual microscopes and zoom in even further to the physical structure. See, hardened cement paste isn't solid. Not really. It's much more like a high-tech sponge with this vast interconnected network of pores. But here's the thing, not all pores are created equal. You've got 2 main types. On one hand, you have capillary pores. Think of these as the superhighways. They're the bigger voids that let water and aggressive chemicals just race right through the concrete. Not good. On the other hand, you have gel pores. These are the tiny, tiny back alleys, and they're actually an essential part of the glue that holds everything together. And this isn't some new idea, by the way. This whole concept was pretty much established by a pioneering cement scientist named T.C. Powers way back in the 1940s. He's the one who figured out that about 1/3 of the pore space is made of these tiny gel pores, while the rest are those larger, more problematic capillary pores. His work was so foundational that it's still what we build on today. Okay, hold on, because we're about to go even deeper. We've seen the soup, we've explored the pores, but what about the water itself? It turns out water inside concrete isn't just, wet. It actually exists in 4 completely distinct states, and each one has a profound impact on how concrete behaves. Let's break this down, because it's wild. First, you have capillary water, just sloshing around in those big pores. If it leaves, no big deal. But then you have adsorbed water. This is a super thin film of water clinging to the surface with a binding gel. You remove that, and the whole structure starts to shrink. Then it gets really serious. You have interlayer water, which is trapped between the layers of the gel. Pulling that water out is like yanking the pillars out from under a building. The layers literally collapse, causing massive shrinkage. And finally, you have bound water, which is chemically locked into the structure itself. You'd need some serious heat to get that out. So how can we even picture this? Well, the main binding agent in concrete, let's just call it CSH for short, it has this incredible sheet-like structure. Seriously, think of it like a sandwich, or maybe a stack of lasagna noodles. This structure is what allows water to get trapped on the surface of the sheets and also between the layers. So now you can see why pulling out that interlayer water is so catastrophic. It's like ripping the cheese and sauce out of the lasagna and watching the whole thing just collapse on itself. Okay, we've been deep in the weeds, right? Chemical soups, nanometer-sized pores, 4 different kinds of water. Let's pull the camera all the way back out and talk about why any of this microscopic stuff matters for the huge bridges and skyscrapers all around us. For a long, long time, there's been this leading theory in concrete science about a weakest link. It's called the interfacial transition zone, or ITZ. The idea is that it's this thin, extra porous layer of cement paste that forms right around the rocks and sand in the mix. And for decades, people have believed it's where cracks love to start. But you know how it goes in science, right? Nothing is ever completely settled. There are some researchers now who are pushing back on this, arguing that this so-called ITZ might not even be a real feature in actual concrete. They think it might just be an artifact, something created by how we cut and prepare tiny samples to look at under a microscope. The debate is still going. Now, I want to show you just one number. And this number, you could argue it's one of the most important numbers in the entire world of cement chemistry. It governs a fundamental trade-off right at the heart of making strong, durable concrete. The number is 0.42. So, what's the deal with 0.42? Well, it's the magic water-to-cement ratio. See, for every pound of cement, you need about 0.23 pounds of water just for the chemical reaction to happen. But you also need another 0.19 pounds of water just to fill up all those tiny little gel pores that get created in the process. You add those two together, and you get 0.42. Any less water than that, and you physically can't hydrate all the cement. But, and this is the incredible part, this is the great paradox of modern concrete. We know for a fact that to make the strongest, most durable, longest-lasting concrete, we almost always use a water-to-cement ratio that is below 0.42. We are intentionally starving the reaction of the water it needs. Why on earth would we do that? Well, it's because any leftover water creates those big, weak capillary pores, those super highways for bad stuff. So we make a trade. We leave some cement unreacted to basically act as a filler in exchange for minimizing that dangerous highway network. So think about that. We make our strongest, most enduring material by deliberately leaving it incomplete. It is a fundamental compromise made at the molecular level to get better performance at the macro level. It really makes you wonder, doesn't it? What other hidden trade-offs are built into the very fabric of the world all around us?